So, good evening, everyone. I'm Saurav Sahu, fifth year PhD student in the Department of Material Science and Engineering, IIT Delhi. So here I'll be taking this special PMRF TA session on the Phase Equilibria course, floated for July 23 session. So for this week, we'll be speaking about the basics of phase equilibrium and some of the fundamental thermodynamics that are necessary for understanding the phase or concepts of phase diagrams. Okay, so I'll be reviewing the concepts that have been covered in this week's lecture. Okay. So starting with the equilibrium. Now, what is the meaning of equilibrium? So when we say equilibrium in this course, we generally refer to the chemical equilibrium between different phases, and this idea comes from the original thermodynamics idea that was proposed by Willard Gibbs in his iconic work on equilibrium of heterogeneous substances. So if someone is interested, they can just go through this work. It's where all of the field of phase equilibrium derives what it is today. So when we say equilibrium, we mean that well, there is no appreciable change whenever we allow a sufficient time parameter to the system. So this is a very fundamental concept upon which the whole phase rule and the phase diagram is based on. So it can be recognized by this following criteria. So how do you know that you have achieved equilibrium? So we have certain rules for that. So the criteria that that have been mentioned so as to identify if the system is in equilibrium are that the properties of the system do not change with the passage of time. And here the time parameter has no limits. So when I say what's the scale of time, it can be it's a matter of minutes, it can be hours, days, or if you see in the grand scale of phases, it can be even million years. So for example, classes, we all know that classes are not actually a stable phase. The ultimate fate of a class is to crystallize, provided you have sufficient time. So in that scale of things, we surpass millions and billions of years, and in human time span, or for all practical purposes, we can consider it as a equilibrium phase, but in true meaning, they are all non-equilibrium phases. So the first and foremost criteria is that the properties of the system, or rather the state of the system, do not change with the passage of time. Okay, and then the state that we are referring to can be obtained by approaching the condition from more than one direction. That is, we will have certain variables in our hand which we can configure, and we can reach to that state in more than one ways. So we can get um, um, let's say ice from liquid by either freezing, lowering the temperature, or we can also play with the pressure and we can convert the phase of the ice. So ultimately we get from state A to state B from more than one pathways by different variables, by playing with different variables. That's how we do it. Well, the whole idea of equilibrium is given by Gibbs free energy equation, which is covered in this course. So just to review, so how we define equilibrium is when equilibrium is defined as the condition when G is a minimum. For a particular set of external conditions. And what are these set of external conditions? When we have pressure, temperature, and composition, and when there is a change in either of this composition, resultantly my G, that is my Gibbs free energy, it will also reflect change. Changes, and the direction of the change will be towards new minimum. And as we said that G is minimum, so if we change the variables, and if what will happen is that my new free energy will move towards the new minimum value, and that will be my equilibrium or my new equilibrium. Okay, so as the equation in mathematical form, the Gibbs free energy is a function of independent variables in this case, independent variables, we take temperature, pressure, and the composition, and can be represented in a differential form as dg is equal to dp minus sdt plus summation of ui dx, where V is the volume, P is the pressure, S is the entropy of the system, T is temperature, and mu I is basically the chemical potential of the phase I, and chi I is the mole fraction of phase I. Now, this value of I that we say here, it has a range from 1 to C minus 1. Now here C is the number of minimum components necessary to define the system. So by just looking at the equation, we can say that there will be a case when, let's say for a monocomponent system where we have C is equal to 1, this term will be disappearing, right? Because we will have C minus 1 as 0, so this term disappears, and what we will be having is just this equation. However, if there is more than one component, for example in binary or ternary or quaternary components, we will be having the effect of the chemical potential of the individual components, and that is and all those will also affect the free energy. So we have described this equation, and also we now know that for a single component system or unary component we have this simple relation. Now we can see how we have reached to this equation. If I just quickly review how we get this equation. So it's known from the free energy equation from the elemental thermodynamics that G is equal to H minus T Ace, where G is the Gibbs free energy and H is the enthalpy, T is the absolute temperature, and S is the entropy. Okay, now if we just take a differential on both sides, what we'll be having is and by chain rule we know that differential of a product is into partwise product of partwise differential. So basically we'll be having S dt minus d ds, and since we'll see that since H is equal to U plus PV, where U is basically my internal energy. So where we'll see where do we get this relation from, but for the time being, since we know H is equal to U plus PV, so if I just plug in the equation in here, so dH will be du plus PdV plus VdP. Now what's du again? Du in again can be written from the first law of thermodynamics as delta Q minus delta W, and if we have infinitesimal changes. So and we know the relation between the entropy and the heat as S is equal to delta Q by T. So delta Q is equal to T ds minus PdV. Now when we say this work, this is actually the work that we do at constant pressure. So here we won't have a dP term, right? So this comes from the first law of thermodynamics. We'll come to that, how we get this equation. So when we just plug this equation in here, what we'll be having is dH is equal to T ds minus PdV plus PdV plus VdP. Minus SdT. And if I just cancel all the terms, what will be remaining is dG. This was dG by the way. So dG is equal to VdP minus SdT. So this is how we reach to this point. Of course, this is we have a set of assumptions that we take here, that is just valid only for a single component system, and so now we'll see that we'll see that this dG value that we calculate now what's this dG is that we will be calculating is actually the available free energy, and it's kind of a driving force for reaction. So, and when I say driving force, so what will happen for spontaneity, to happen, or for a spontaneous reaction? The free energy must be negative. And philosophically, it makes some sense, because if uh, a reaction happens by its own, that's what we mean by spontaneously. That is, there is no external driving force for the reaction. So if it is happening spontaneously, it should only move towards where it can be more stable. So nature always prefers lower energy, because higher energy is associated with instability. So for a reaction to occur spontaneously, the state must move towards the direction of lower energy, and that's how we have a lower value of free energy towards the ends, and that is the reason if we take the difference. And whenever we say dg, or whenever we say difference, so in thermodynamics we always take the final minus initial state, right? So if this is negative, that means I am ending up with a lower value than what I'm started with. So if my energy is ultimately lower than what I have started with, well, I have successfully minimized my energy. So that is how my free energy is getting lowered, and that is how I have moved towards a more stable state, right? So this is what we have for spontaneity while at equilibrium. So when we say equilibrium, we have seen in the first slide that at equilibrium there should be no change, right? So the system has to so system should not change from its states. There should be no appreciable change in the time span that we are seeing with the passage of time. So basically, at equilibrium, free energy should be equal to 0. So no further changes could occur. And there's a reason why we take the free energy as a basis for the phase diagrams, and not different parameters. Like in thermodynamics, we have the Helmholtz free energy, we have the internal energy U, and so why do we take G and not these other energies as a criteria for our phase diagrams? Well, because it turns out the other thermodynamic parameters, like the Helmholtz free energy or the internal energy, these are just another combinations of dependent variables. And practically speaking, from an experimental standpoint of view, this G is basically dependent on the pressure, as you can see in this equation. So it depends on the pressure, the temperature, or in the case of multi-component systems, it also depends on the chemical potential, right? Or the mole fraction. So basically, it only depends on the value of the free energy. Gibbs free energy depends on the pressure, the temperature, and the composition. That's the mole fraction. And these are easy to manipulate experimentally. This is the reason why we take the Gibbs free energy as the basis for our phase diagrams. Just because we can not only calculate it theoretically, but also we can do some experiments and we can cross validate. Although the experiments, most of the phase diagram that we see It's pretty hard to reproduce experimentally. Okay. So coming over to some basic concepts. So what do you mean by a system? Now that we have started thermodynamics, we should know some fundamental technical jargons that we'll be speaking. System is a portion of the material universe which can be isolated completely. And arbitrarily. For consideration of changes. Which will occur within it. Under varying conditions. So in thermodynamics, what we'll be having is a system and a surroundings. So anything that's not a part of the system will be considered as the surrounding, and the system is the part which is under study, and that is how we isolate this, and that part of the universe we isolate it and we study it, and the whole combination of the system and surrounding will give you the material universe, right? So there are different types of system when we speak about thermodynamics, so we'll just quickly go through them, what are different types. So we'll be having isolated system, we'll be having closed system, and we'll be having an open system. So what do we mean by isolated system? In isolated system, no work is done either or on the system or by the system. So neither the system is doing any work nor we are doing any work on the system, and there is no energy transfer as well, right? And this is just isolated completely from the entire universe. So there is no work done on or by the system, and there is no heat, energy, or matter transfer. So when we transfer, when we say transfer, it can be either, so we are transferring energy to the system or matter to and fro the system. No, matter is the components of the system, right? So in closed system, it is diathermal but impermeable. Now what do we mean by this? Diathermal, so in closed system, what happens is diathermal refers to the state where we'll have, so diathermal refers to the state where we can have free heat exchange from the system to surroundings and vice versa, that is from surroundings to system. So the heat flow occurs both ways, that's a diathermal, but it is impermeable. That is, we do not allow any transfer of mass either from outside to inside or inside to outside. A best example for this could be, let's say, water kept in a metal bottle. So best example for this could be water kept in a metal bottle. So if we have water in here, so in this case, since it's metal, you know, the heat can easily flow in and out of the system. If the bottle was water was initially hot, it will be in equilibrium, thermal equilibrium with the surroundings, and we will have free exchange of heat, but there will be no mass flow. That is, the water that's here, it can't go in or out of the system, right? Nothing can go in or out of it. It's a closed system. Similarly, what's an adiabatic system? Now, when we say adiabatic, it means that the heat is conserved. In this case, in adiabatic system, a best example is an insulated water bottle. Right? So in insulated water bottle, what we'll be having is we'll have, so this is an insulated bottle, so we'll have insulated walls of glass around the entire bottle, and this will not allow heat to flow into or out of the system. So this is an adiabatic system. And in the case of an open system, right, so in open system we have diathermal case as well as permeable case. So example of this could be let's say water kept in a glass. So we have heat flowing in and out of the system, as well as we have the evaporation happening from the auxiliary surface. So we have mass exchange as well as heat exchange. So this is how we'll be having both transfer of mass and heat, and this is an open system, open thermodynamic system. Okay, so now that we have defined system, we'll come to what is a phase. So what's a phase? A phase is a portion of a system which is physically homogeneous within itself and it's bounded by a surface so that it is mechanically separable from any other portions. Okay, so when I say physically homogeneous, that means it will have physical properties which are same throughout the entire phase itself. And if we go from one phase to other, we'll be seeing that we'll be crossing or rather we'll be seeing certain differences in the physical properties. So that's how we know that we have crossed over the boundary and we have moved to a different phase. And it will be having a surface or an interface such that it can help us to distinguish between different phases. So let's say a best example which I can take to explain this is composites. So in composites we have matrix and reinforcement, right? So let's say if we have a ceramic matrix composite or a metal matrix composite, anything. So we'll be having certain dispersed phases which we call as reinforcement, and it can be in different geometries. It can be globular, it can be platelet shaped or so. Anyway, so yeah, so you can see that this generally we have different characteristics of the whole purpose of compositing is to have net material or composite material such that the property is better than the individual phases that we've taken. So if we have phase 1, this, and this is the phase 2, so my net property of phase 1 plus 2 generally should be better, a given property, right? So yeah, so in composites we'll be having two different phases, and how we know that is that because the structure varies. So if I go from this part to this part, we'll have a difference in the physical structure. And importantly, what we also should consider is that there will be a boundary between the two phases. Now when I say boundary, such that we have a sharp distinct interface wherein we can cross to go from one phase to other, and this is how we can distinguish mechanically, either by optical micrographs or by certain other mechanical process. We can see that one phase is separable from other phase, and this is the region that we call as interphase, and for all practical purposes we summarize it as interface. So this is how the word comes, interface, right? It's nothing but interface between the two phases, the boundary. So composites, and these are very important parts of the composites, by the way. So we have a matrix part, we have reinforcement, and we have the interface. So the properties of the interface also play a very important role in determining the roles, the properties of the whole composite. Let's say if we have a weak bonding at the interface, we'll have delamination and such issues. So yeah, so this is technically what we call as phase. And when we talk in phase diagrams, the phase that we'll be talking about is can be characterized by the structure. So the physical structure is how we characterize the phase, even though with the chemical component could be same. For example, let's say if we have a combination of let's say we have a system here, and we have ice cubes floating in it, and remaining is water. Right, now we all know that this both can be represented by the same chemical formula, that's H2O, but the structure, because this is a solid form of water and this is liquid, right? So we have a difference in structure, so this can be now qualified as separate phases. So hi Gautam, can you hear me?
Yes, sir.
So I guess you joined a bit late, so I had already started explaining a few concepts related to this week's courses. So I don't know, like, did you go through this week's content? Hello. So what I'll do is I'll just go through the contents that I have prepared. So in the meanwhile, if you have any doubt or if you have any questions regarding this week's content, so you can just unmute yourself and ask me those. So I'm recording this meeting because the time is supposed to be 6 p.m. to 8 p.m. So I have started directly at 6. So I'll be also sharing the recording what I have covered earlier, and you can go through it. If you have any doubts, you can always come back to me, right? So I was speaking about phase. Now, what's a phase? So I'll just quickly recap it for you. So a phase is a portion of a system which is physically homogeneous within itself, and it is bounded by a surface. So what we'll be having is that if you have a combination of phases in the system, how we'll recognize the different phases by the physical structure, and the phases will be separated from each other by a boundary that we call it as interface. And this interface is an interface play a very important role in, let's say, in composites and so system. And yeah, and the identity of a phase is preserved by their physical structure, even though their chemical nature could be same. So chemically they might be similar, but physically distinct. And I had taken the example of ice in water. So in ice is also chemically represented by the same chemical formula, and however by structure they are different. That's how we have two different phases in the system, right? Okay, so now, okay, now I'll just go through components. Now, having described phase and a system, now what we come down to is the component. Now what are the components of the system? So component of the system are the smallest number of independently variable chemical constituents necessary and sufficient to express the composition of each and every phase present in the state of equilibrium. So uh, so since we have defined what's equilibrium, we'll have certain phases which are existing in equilibrium, and how will we describe that phase? We have to write a chemical equation, right? So, and the minimum number of chemical components that we can use to describe the whole state of equilibrium is the number of components. For example, let's say if we have chemically, if I have a system of calcium carbonates, and it exists in equilibrium with the calcium oxide and carbon dioxide, and that's a gas, right? This is solid and this is solid. So at equilibrium, all the three components, that is calcium carbonate solid, the calcium oxide solid, and the carbon dioxide gas, are present, but they are not all they all three of it can't be considered as the components, right? we can't just describe the whole state of equilibrium by taking the chemical formula of CaCO3, CaO, and CO2, since they are not independent. So in this case, we'll see that if we just take any two, so if we just take any two chemical constituent, the remaining phases can also be determined. Now how? So for this equation we have written so what are the possible chemical components we can have? First of all, the whole parent material, that is calcium carbonate, calcium oxide, and carbon dioxide. These are the different phases that we have, right, in this system. And what are the different chemical constituents that we can take? What are the chemical components? The components can be carbonate, oxide, carbon dioxide, and calcium carbonate plus carbon dioxide. So to describe calcium carbonate, if we take the components, okay, to describe carbon dioxide, if we take the components as calcium carbonate and calcium oxide, well, if we take calcium carbonate, it itself can describe its phase, right, its own phase. So if I represent it by a plus, and if I take calcium oxide, right, calcium oxide cannot give me calcium carbonate, so I cannot take this. I'll represent it by a 0. Calcium carbonate can be represented by calcium oxide as a component. The phase of calcium carbonate can be represented by calcium oxide as a component, so plus. But calcium carbonate cannot give us calcium oxide. We cannot represent calcium oxide by taking calcium carbonate as a component, so this will be 0. And how will we get carbon dioxide from these two components? If we just subtract them, right, Ca, if we just subtract CaO, we'll get carbon dioxide. So if we take plus CaO and we subtract minus CaCO3 and subtract CaO from it, we'll get CO2. And yeah, and let's say in this case, if we have calcium carbonate and calcium oxide, to describe calcium carbonate phase, we need calcium carbonate component, right, but carbon dioxide is not needed. Similarly, for calcium oxide phase, we just need to subtract this both, right, and we'll be having calcium oxide. And to describe carbon dioxide, well, we already have carbon dioxide itself as a component, so we can describe it by so we can describe it by itself. So yeah, and yeah, in this case, calcium carbonate and calcium oxide, how will we get calcium carbonate? If we just add them up, right, we'll have this two. And how will we get calcium oxide? Since it's already a component, we just only have to take calcium oxide as a component and we'll get calcium oxide as a phase. And carbon dioxide, we already have carbon dioxide as a component, we'll have carbon dioxide as a phase. We don't need calcium oxide for this. So we can see that each of the combinations of this chemical constituents, that is calcium carbonate plus calcium oxide, or calcium oxide plus carbon dioxide, or calcium carbonate plus carbon dioxide, can individually or independently be taken as the components of this equilibrium system. However, it's more if it is more convenient for me to just take this one, because then I don't have to subtract anything, right? I just don't have to subtract anything. I just have to add it up to get all the phases present in my equilibrium system. Okay, so these are all can be taken as all pairs. They qualify as components of the equilibrium reaction. Okay, so now that we have already established the technical the technical aspects of it, so now we will see how how we can study more about internal energy. Now I'll quickly go through what's internal energy because it's not actually covered in the lecture, and to describe the specific it and so, like, we need to know what's internal energy. So in this case we'll take an example of a system of a thermodynamic system which simultaneously performs work and absorbs heat, and it does that simultaneously. So for example, let's say we just have a basic piston containing ideal gas. It's a simple system, and we have some weight on this. Okay, and this is my pressure and this is my volume, and we have a temperature. So this is a simple system gas in a cylinder. So let's say this system simultaneously performs work. Now when we say perform work, that means it is doing work, and conventionally we treat when work is done on the system, the convention is negative, and work done by the system the convention is to take it positive. Okay, so first we'll take in the first part we'll consider that only and only we perform the work and there is no absorption of heat. So when the system performs some work, there is a change in internal energy. Now what is this internal energy? Internal energy, U, is also described as a thermodynamic potential. Is a thermodynamic potential, and it basically depends on the kinetic and potential energy contributions, right? So when the system is doing any work, so it has to expend some of its internal energy, right? So let's say if we have initial state, we have the internal energy as Ui, right? And in the final state, we have internal energy as UW. Now W here signifies worked, that it has already worked. Okay, so Ui and UW. So if it has done some work, there will be certain change in my internal energy, and that internal energy is none. And thermodynamically, as I have mentioned, all the values are taken from final to initial state difference. That is, if we take the final to initial difference, we will be having UW minus UI, right? And this difference in the internal energy um, is equal to the, because this amount of internal energy has disappeared from a system and it has appeared as mechanical work, and this is the mechanical equivalent of heat. So this amount of energy as heat has disappeared from the system and has appeared as a mechanical work given by W. So and this W is my mechanical work, and that is represented by EdV. And it's easy to see if we have, let's say, a difference in volume and, for work done at a constant pressure. So we can see that the difference in the volume into the pressure will give us the work done, right? So thermodynamic work done for constant pressure will be integration of P dV from V1, let's say the initial to W, that is after worked, and by convention we write it as minus integration of P dV minus W, or W is equal to minus delta U. Okay, so this was the case where we have done the mechanical work. So work performed by the system by expanding the internal energy. Okay, so this is the condition of the system after the work the machine, or this term, sorry, not the machine, the thermodynamic system has done some work. Now what's the now what's the case after it has absorbed some heat? Now I'm separating them both. So now when my thermodynamic system absorbs heat, right? So initially I'll have let's say my initial because in my because here we have said that it simultaneously performs work and absorbs heat, but we have considered that the two to happen one after another. So in this first case we have assumed that the system has performed the work, and then secondly we will independently assume that it has absorbed the heat, so as to see what's the, because ultimately we'll see that it's a state variable, the energy is state variable, and the path taken by it, um, yeah, it's path independent, so we don't, it doesn't depend, uh, it's not dependent on the fact that we actually do the work first or absorb the energy, or absorb the energy or do the work first. So in this case we are assuming that first it has done the work and then it's absorbing the energy. The initial state will be UW, because the final state for this part will be the initial state for this part, and U final, let's say, will be UF, right? Okay, so throughout the whole process my delta U, so this was delta U1 and delta U2 is U final minus initial, so UF minus UW, right? And this will be equal to my heat that it has gained. Okay, and this amount of heat that it has gained will appear as the increase internal heat increase due to absorption of heat energy, right? And well, since we said that this whole this whole system does work and absorbs energy simultaneously, and we have considered them independently in this case. So if it happens simultaneously, or simultaneous for simultaneous work and heat energy absorption, we'll have U total, that is equal to delta U1. So delta U total is equal to delta U1 plus delta U2. The delta U1 was independently when the system has done some performed some work, and delta U2 when it is the case when the system has absorbed some energy Q. So we have seen in the initial part the delta U total is equal to del U1. So the value of del U1 here was UW minus UI, and if we just add it up, plus UF minus UW, right, and we'll just cancel it up, we'll have UF minus UI, and that will be equal to, and if we have the RHS term, we add the RHS term, we have minus W here and plus Q here, and if we just add them up, we'll have plus Q minus W. So delta U, no, I'm not writing total because I have considered the whole thing, the whole reaction to be simultaneous. So delta U is equal to plus Q minus W. So this is what the first law of thermodynamics tells us. The amount of internal energy is used to perform work, and the heat energy that is absorbed increases the internal energy. Okay, so now that we have seen that from the first law of thermodynamics that we have an increase in the internal energy, or rather we have a change in internal energy because of simultaneous heat and work that is happening, that is either done by the system or that is the energy absorbed by the system. So graphically we can represent it as, because I have mentioned that it's a state variable. So internal energy is a state variable. When I say that, so let's say we have a so we have pressure and volume here, right? So in the initial part we have said that we have considered a simple thermodynamic system with a gas contained in a piston, right? So we have a gas that is contained in a piston W, and it had some pressure, volume and temperature, and after doing some work we'll be having certain difference in the pressure, volume, or if considering one or two of the thermodynamic variables to be constant. So in this case we have that we had initial state wherein we had PI, VI, right? And in the final state, we'll be having PF, VF. These are the coordinates of representing the states of the equilibrium states of the system. And the way it has gone from this I to F is by uh, is either by some work has been done on the system. So in this case, let's since we see that the volume Vf is less than Vi, that means some work has been done on the system, right? So it's minus W. Anyways, so we can see that this U, so this correspondingly the change in internal energy will be UF minus UI, right? So it will only and only depend on the internal energy or the initial and final states. So it is independent of the path. Independent of the path followed. And this is a characteristic property of all thermodynamic state variables. It only and only depends on the initial and final states, right? The state variables. However, if we have now, since we also know that there is a correlation between internal energy and the internal energy and the work and the heat energy. So we'll tell U is equal to plus Q minus W, right? We have seen in the previous slide. So so this amount of heat or work, now it can be done. So I can either bring the system from initial to final state by this route, or you can bring the system from initial to final state by this route, right? So, or you can either bring the state from the state by this route, and so on. Now, what it technically means is that the work done will be different. So in this PV diagram, if I have something and if I just take area of it, right, the integration of P delta V will give me the work done for a constant pressure. So in this chart, in this reaction coordinate, if I just take the area and then it will give me the work done, and we can see if the work if the transition happens from the initial to final state by this route, the area are not the same, right? So in this case, if you see the area 1, and if we say, let's say we have this one, this is area 2, right? So area 1 is not equal to area 2. So that tells us my delta W, the infinitesimal work that has been done on the system or work performed by the system is not a state variable. Now, very important for us to remember that even though it's not a state variable, but we are still relating with the thermodynamic state variable of internal energy, and so is the so do we do for the heat energy that subs out. So it's kind of interesting to see that the combination of two non-state variables gives us a state variable. And if you write in differential terms, you can write like this. Okay, so W is not a state variable because it's essentially in this PV plot we can see that's an area, and area 1 is not equal to area 2. Therefore, the work done is not is actually part dependent. The work done is part dependent. Hence, not the state variable. Rather, it's written here. So since it's path dependent, hence it's not a state variable. Okay, so now that we know from the first law of thermodynamics that the internal energy is increasing upon absorption of heat, and also the internal energy decreases upon if there's some work that is done by the system. So now we'll go to quickly determine the constant volume and constant pressure processes. Now, since we had already told that in Gibbs free energy we have three parameters, right? We have the temperature, pressure, and the composition, and all three of it can't be kept. We can't keep on varying all three because it's in some of the processes you will see that we'll have to kind of keep one of them constant and then vary some of it. So let's say in constant volume process, what happens is the volume of a simple system. Now, simple system, you can consider the example that I have shown earlier. That's ideal gas in a piston. So, volume of a simple system is maintained constant. Volume of a system is maintained constant. So, as we have seen, the definition of work is the P dV integral of P dV from V1 to V2, and since the volume is constant, it's 0. Now, if it is 0, so what we will be having from the first law of thermodynamics is this turns to be 0. Therefore, all of my heat is changing the internal energy, right? So in the constant volume process, everything is the change in internal energy is only and only dependent upon the heat. So heat, because there is no mechanical equivalent of heat, or there is no work, there is no mechanical work. That is associated in this constant volume process, right? So this is how we have it, and to get the so this Q is represented by Q subscript V, representing constant volume. So if we just take the integral, I think we can get a total amount of heat that is there. And in constant pressures, similarly, constant pressure process, we have W is equal to PdV integration from V1 to V2, and since pressure is constant, we can take it out. Is equal to P V2 minus V1, and this amount of work is actually affecting my internal energy as well. So from the first law of thermodynamics, I know my delta U is equal to U2 minus U1. considering u2 as the final state initial system and u1 is the initial initial system, is equal to delta q, that is the amount of heat that has exchanged during this whole transaction, minus delta w, and this delta w in this case was v2 minus v1, right? So if I just expand it, what I will have is so it will have, if I just take this on the left hand side, u2 plus pv2 minus u1 plus pv1 is equal to delta q. Now you can see that since v is a state variable, u is also a state variable, and it's a combination, it's a linear combination of a state variable. So, and this itself kind of a linear combination of state variables. It's itself a state variable. Right? And what is this new variable we have now? So u plus pv is what we call the enthalpy. It's the enthalpy of a system, and it's nothing but the amount of energy plus the pv term. So we'll see for condensed phases, as Professor Garg has also highlighted in his lectures, for condensed phases my PV term is very small, right? So it can be practically taken as 0. So all of my enthalpies comes from the internal energy of the system. Okay, so if I just take the integral of it, what we'll be having is applying the chain rule that we had done earlier. And since here the pressure is constant, the dP terms go to 0. So we have du plus pdv, right? So in a nutshell, what we will be having, the delta H is equal to delta Q P, right? Now delta H is this part. So this is H2, because you have considered this as H, so this is H2 minus H1. So better if I write it here, H2 minus H1 is equal to delta Q, which implies delta H is equal to delta Q, and since this reaction is occurring at constant pressure, subscript P. So this is very important if you are dealing with heat, specific heat capacity or specific heat at constant pressure, constant volume. So in this case, what we see is that under constant pressure, process enthalpy change is equal to heat exchanged, right? Okay, so since in the lecture it was also mentioned, but we didn't actually go through the specific heat. What is specific heat? The specific heat is actually the amount of heat that is required to change the value of a temperature, value of the temperature of a body by unit degrees, right? So since the thermodynamic parameters are intrinsically linked, so let's say we have pressure, volume, and temperature. So if I am increasing the temperature by unit degrees, 1 degrees Kelvin, let's say 1 Kelvin, So if I increase the temperature of the system by 1 Kelvin, I have to correspondingly there will be certain change in the pressure and volume as well. So one of them I'll have to keep as constant. So either I'll have to keep both of them as both of them as variables, or I have to keep one of them constant. And practically what we do is we take specific heat, or the heat capacity rather. So specific heat is when it's in intensive property. I'll come to that. So its heat capacity, since it's associated with rising temperature, so it can be done in two ways. It can be done at constant volume way, or constant pressure. Right. So if it is done in constant volume, what we'll have is CV. So does V denotes the constant volume, is del QV by T, and from our calculations we have seen that with constant volume delta QV is nothing but du, right? So this is du by dt at constant volume. And similarly, in specific heat at constant pressure, we'll have the enthalpy, right? Because in our calculations we have seen under constant pressure we have delta Q is equal to delta H. So delta H by delta Q at constant P. Okay, so now that we have covered the things which were briefly mentioned in the lectures in quite detail, okay. So now that we have covered the things which were covered in the lecture in quite detail, so now we'll just go through quickly, because now since we are talking about specific heat, so we have seen that how specific heat at constant pressure varies with temperature. It's also mentioned in the lecture, right? So it's important to know how it varies, because that's the way we can see, or we can understand the trend of the free energy with temperature. So Cp, if we see how it varies with temperature, so this will be something like this, some sigmoidal curve, and Cp is the constant pressure, since I've written in the previous slide, the amount of heat required to raise the temperature of the body by 1 Kelvin done at constant pressure, and it's equal to the enthalpy, the differential enthalpy by differential temperature at constant pressure. And so if I just take this in differential to this side, what we'll be having is, since Cp is equal to dH by dt at constant pressure, therefore dH is equal to Cp dt, or H is equal to integral of Cp is the constant, so dt outside from 298 to T. And here why 298 is, maybe I can just do it stepwise. So if I just integrate both sides, so I'll be having so for phase equilibria, what we assume, in phase equilibria we assume that for pure substance at 0 Kelvin, sorry, at 298 Kelvin. So for pure substance at 298 Kelvin, that's 25 degrees centigrade, my H is equal to 0. Therefore, since we are talking about equilibria, there is a phase transformation. So my initial part is my enthalpy at initial room temperature, and this is taken as 0. So my final enthalpy will be H, because delta H, the initial H1 we have taken as 0, so H is equal to simply the integration of the specific heat to temperature starting from 298 to the final temperature where we are, where we observe the um, phase transition. And if I just plot it on a graph, should be something like this. And this offset tells us that this H is equal to 0 at 298 Kelvin. This is negative. And since if you equate it, since it's quite curved, but you can equate it to a straight line, at least in the smaller portion in the positive side. So this part, if you just equate it to y is equal to mx, so here the slope will be Cp, right? So the slope of my h versus t curve gives me a specific heat. And how can we get the entropy? So from thermodynamics we know Cp by T is equal to dou S by dou T at constant pressure. Now how do we come to this? We have seen in the previous slide that Cp is equal to dH by dt at constant P. So I just plug Cp here. Cp by T will be dH by dt, and we know that dH is equal to dq, constant pressure process. We have seen that dH is equal to dq, the enthalpy change is the heat change, so delta Q, because we are all dealing at constant pressure. So dH is equal to delta Q. Now we write d and delta because Q is not a state variable, so we can't write dq, rather we write delta Q. This is format notation. So it's a state variable, enthalpy is a state variable, so that's why we write d and not delta. So dq by t, dq by dt, t, and this dq by t is itself what second law of thermodynamics gives us a beautiful thing. We call it the entropy, and it's the entropy dS by dt or dou S by dt. So this is actually the entropy change of temperature at constant volume, constant pressure, right? So from this I can get the Cp by T is equal to dS by dt at constant P. If I just take dt at that end, and if I integrate it from 0 to T, what I'll be getting is actually the entropy. Right? And how this entropy varies, pretty much similar to how Cp varies. We'll have a sigmoidal curve like this. And this is how the entropy varies with the temperature. Okay, and since in the initial part we have derived this relation, a very interesting relation, VdP minus SdT, which is nothing but my free energy. So I can just plug in those terms in here and I can actually find the value of the free energy from these two graphs, right? So at constant pressure, So dg is equal to vdp minus sdt. So at constant pressure this will be 0. Therefore dg is equal to minus sdt, which gives me that my free energy change with temperature is negative of the entropy. That tells me that if I increase in temperature, my free energy will be going in opposite direction for a constant entropy. That is, I'll have a negative slope. So it's very important. So what I'll have is something like this. So this is my enthalpy curve. This is my free energy curve, and this is Ts, the difference between them is Ts, is temperature, and this is basically my energy or enthalpy, because we are considering the positive side is enthalpy, so we take as enthalpy. This side is the free energy, and the slope. So this is how the slope of it, is negative of entropy. So and we have seen in the lectures that if there is a phase transition, there is a there will be a certain increase in the enthalpy. Correspondingly, the more stable phase at that temperature, there will be a change in the free energy. It actually proceeds towards a more negative free energy curve. For example, taken was, if you take a transition from solid to liquid, so there will be certain latent heat of fusion that is required, or melting temperature. This is the melting temperature, and there will be certain change in the enthalpy, and then correspondingly we will have more negative free energy corresponding to the free energy of liquid, which is stable at T greater than Tm. So maybe I can quickly summarize that as well. This is H liquid, this is H solid, and this is G solid, and this is G liquid. Right. So at this point where it intersects is actually the critical temperature of transformation that we call it as, in this case, solid to liquid melting. It's the melting temperature. Right. So at this point, what happens is at T than Tm, my G liquid becomes lower than G solid. Right. You can see that the red curves is below. It's more negative than G solid. So that's why my liquid is stable. It's in stable equilibrium. And at lowest temperatures, my G solid, you can see G solid is lower than G liquid. So my G solid is actually lower than liquid, so solid is stable. So now let's see what happens if we just heat it up. So if we heat it up, the enthalpy goes on increasing. Enthalpy goes on increasing this way, and at the melting temperature, it keeps on absorbing the heat. Keep on absorbing the heat, and it will change the portion. So this is how it goes. So this part, the absorption, is the latent heat of fusion. And since we have described that specific heat is the nothing but the specific constant pressure is nothing but the derivative of the H versus T graph, right? So in this case, the H versus T graph is this, and if we take the derivative, we can see this is the we can get the heat capacity when it's in solid, but the moment it transfers from solid to liquid, we have a curve like this. So at the moment of phase transition, we have something like this, right? So you can easily see that the slope is 90 degrees, and if we put it, it's infinite. So in this case, the Cp is infinite at phase transitions, phase transition temperatures. And this happens because if you think philosophically, at the phase transition temperature, in this case the melting temperature, my material will keep on absorbing the heat. So it will absorb the heat, and whatever heat that is that it is getting, it will keep on absorbing, and it will not allow the system of the temperature of the system to increase. And the whole purpose of specific heat is to calculate the amount of heat required to increase the temperature of the system by unit quantity. But all of my heat is not going to the increase in temperature, but rather it is going in the phase transformation. So that's the reason why my heat my temperature is not increasing, my temperature of the system is not increasing, and that's the reason my Cp is infinite. So all of my heat is going in the phase transition process, in this case solid to liquid transition, right? And this is what is absorbing the heat, and we have infinite heat. So it's one of the assignment questions. In this case, there's no doubt that we'll be having infinite heat capacity. So coming on to the another thing, like a small concept, when we say intensive and extensive variables, I missed out in the initial part. So what do you mean by intensive and what do you mean by extensive? So intensive is something which is dependent on the size of the system, or so rather independent of the size of the system, sorry. So it is independent of the size of the system. So let's say pressure, temperature, these are all intensive variables. And extensive is the dependent on the size of the system. So my free energy, mass, etc., volume, these are all dependent on size of the system. So if I have a bigger system, my volume will be more. If I have a bigger system, my mass will be also more, because a number of constant particles will be more. But there is a way of converting extensive property to intensive property. So if I have, let's say, mass per unit volume, which is nothing but my specific density, or rather density, or if I take volume per unit mass, that's specific mass. So in this case, we are just dividing out an already extensive property, which is mass, by volume. So what we'll be getting is density, which is actually not dependent. So when I say density, rho is equal to 1 gram per cc for water, it can be 1 gram per cc for a glass of water, and it can be 1 gram of cc for, let's say, a tank of water as well. So the density is not dependent on the size of the system. Density is just a unit property, right? For unit volume, we have unit mass, and that's what is the intensive property. And interestingly, like if we have from, we know that the ideal gas equation, right, PV is equal to nRT. PV is equal to nRT. The pressure volume is equal to number of moles times the ideal gas constant times temperature. In this ideal gas equation, if I just divide it by n, so since we have said that the volume is a extensive quantity, but if I just divide the volume by n, which will give me P V dash is equal to RT, where V dash is the volume per mole And this, since volume is an extended quantity but we divide it by the number of moles, the volume per mole is actually an intensive quantity, or it's an intensive variable. So it's worth figuring out whether variable that we have been given is intensive or extensive by just correlating it by the change it would undergo if we scale the system to a bigger or smaller size. So if we just scale the mass system, we'll have bigger volume, bigger mass, but the mass per volume, that's the density, is not going to change, given the system or the phase is the same. Of course, if we have a different phase, the density is also going to change there. So Jay, can you hear me? I just see that you have joined here. Well, it's an open class session, so if you have any doubts regarding this week's content in this course, always feel free to speak out. And if you have any queries or questions in my presentation, you can always interrupt me and ask me. So we have seen in the last part of the lecture the Clausius-Clapeyron equation. Right, the Clausius-Clapeyron equation, and there was an assignment to try it out on a phase diagram. So we'll quickly go how we have derived the phase, derived the relation to Clausius-Clapeyron equation. So if we have two different phases coexisting at a temperature in equilibrium, so let's say if we have phase 1 and phase 2 and both have 1 mole of each. So at phase 1 we have dg1 is equal to Vm1 dp minus S1 dt, where Vm is the molar volume of phase 1 and S1 is the entropy of phase 1. And for phase 2 we have dg2 is equal to Vm2 dp minus S2 dt. For both phases 2 coexist at equilibrium, my dg should be equal to 0. That means the net reaction should not proceed in the left or right direction. My system should be in equilibrium. So dg1 is equal to dg2, right? Therefore Vm1 dp minus S1 dt is equal to M2 dp minus S2 dt, which gives me if I just club them in one side, the dp and dp this side, so Vm1 dp minus S1 dt is equal to Vm2 dp minus S2 dt. Right, so Vm1 minus Vm2 dp is equal to S1 minus S2 dt, which gives us dp by dt is equal to S1 minus S2 by Vm1 minus Vm2, which is equal to delta S by delta Vm. And since we know that the change in enthalpy per temperature, and this comes actually from consideration. If we just take delta G is equal to G1 minus G2 is equal to 0, we have delta H minus T delta S is equal to 0, we'll have delta S is equal to delta H by T, right? for both phases to coexist when delta G is equal to 0. So that's how I will get the relation between the entropy and the enthalpy. And if I plug it in here, what we will get is dP by dt is equal to delta H by T delta Vm, right? And this is an important equation that is known as the Clausius-Clapeyron equation. And this tells us that if provided my molar volume change is non-zero between two phases of transition, there will be certain change associated with the pressure, provided there is a change in temperature. So for example, like in the class it was discussed for the different phases of iron, what will happen if we just let's say change the temperature, if we change the pressure of one phase of an iron, so what will happen to the phase transition temperature between the two phases, right? So in the class it was decided, it was determined, like it was asked to apply the Clausius-Clapeyron equation to water phase diagram. So that was a homework, so we'll discuss it here. Right, so how does a water phase diagram looks like? So if you open pretty much any textbook on phase transition, I think you can easily see the diagram of water, so I'll look it up. Yeah, this is how it looks like. Maybe there will be a cleaner version. I guess we'll look at this. So this is how it looks like. Right. Liquid, solid, vapor, the temperature and pressure, right? So let's say if we have one atmosphere here, so the world that we live in is at a pressure of 1 atmosphere. So we all know that in this under these conditions, 1 atmosphere, water or the ice will turn to liquid at 0 degree centigrade. So this is 0 here, and liquid will turn to vapor at 100 degree centigrade, the boiling point. Right. Okay, so what if I have a phase transition node? So if I know that there is a solid to liquid phase transition, and under this condition, so if in this boundary, this both the phases coexist, right? So this 0 degree centigrade, how does this 0 degree centigrade representing my solid to liquid equilibrium changes? How does this temperature of phase transition between solid to liquid changes if I change my pressure? So if I keep my pressure, if I change my pressure, how is this going to change? So this can be answered by this Clausius-Clapeyron equation. So we'll work it out here. So this equation tells us that dP or the change in pressure with change in temperature can be represented by the change in enthalpy by the change in the molar volume. So if we just take a reciprocal of that, just to keep this on the numerator, so T is equal to 273 Kelvin. So we are dealing with the ice to liquid transition. T is equal to 273. So the molar volume of ice is 1.1. We all know that ice occupies more volume, has a less density, and it floats on water, right? And the volume of water or liquid is 1.0 gram per centimeter cube. So straight away you can see that my delta Vm and thermodynamics. So always my final minus initial. What's my final state? Final state is, since we're talking about ice liquid tension, the final state is liquid to ice. Ice was the initial state. So liquid has volume of 1. It has volume of 1.1 gram per centimeter cube. So it gives me negative 0.1 gram per centimeter cube, right? So that means my delta Vm is less than 0, and this tells us that dt by dp is less than 0. Sorry. Since my delta Vm is less than 0, and hence if we go back to the ice diagram, we'll see that the solid to liquid phase transition boundary, right, this boundary has a negative slope. So this dp by dt is less than 0 at this point. The reason is because the final volume is liquid volume is lower than that of the solid volume, or the initial volume. So, and intrinsically the effect of added pressure will manifest as increase in the phase area with lower volume, right? And we know that volume of liquid is lower than volume of ice. So that's the reason why if we add the pressure, what will happen is my phase for if you see, if I add pressure, my liquid area is getting increased, right? So if I just plot it here again, so on added pressure, what is happening is my liquid area is increasing as compared to my solid area. So that can be also applied to the vapor as well. So you can see that upon addition of pressure, the phase with the lowest volume will be more stable as compared to the phase with a higher volume. And since solid has a higher volume and compared to liquid, so my transition boundary between the solid to liquid will shift towards left, such that my phase field of the liquid will be having more area under added pressure. So this was the effect of the Clausius-Capiron equation. So I guess this covers all the topics that were for this week. So we started out with the basic definitions that we had that we have for this course, starting with equilibrium, what's the equilibrium, and the very famous Gibbs free equation. How do we reach to this equation? And then um, what are the different um, technical terms? That is system, what's a phase, what, how do you define the components of the system, and what actually how can you select the components of a system in equilibrium. And then we went on to describe how the internal energy can internal energy is a relevant parameter which deals with the work and heat, and how we can calculate the internal energy of the system for which has done the work and absorbed the energy simultaneously, and this has given us the first law of thermodynamics equation. And then we have seen how the internal energy is a state equation, but the work and heat are not. And as a consequence of which, so we have the constant volume and constant pressure processes, and we have seen how the equations are derived for each of the cases, and we have seen how this constant volume and constant process they apply to the heat capacity, the concept of heat capacity, and how this concept of heat capacity again can be applied to evaluate the enthalpy and the entropy. And from this we have seen that how from these equations we can evaluate the free energy, and the free energy curves can give us an idea about the stability of phases, which are stability of multiple phases under different temperatures. And we have seen that uh, how the variation in the enthalpy, or rather how the variation in the free energy is supported by the changes in the enthalpy, and that's been explained with an example of this simple solid to liquid transition, wherein we will have an increase in the enthalpy but a decrease in the free energy. And then we went on to describe how what are the intensive and extensive variables of the system, and then how certain extensive variables can be converted to intensive variables uh, by dividing with another extensive variable. And then we went on to describe the Clausius-Clapeyron equation. So that describes the influence of thermodynamic parameter upon another thermodynamic parameter in the relation with its molar volume. And we have seen the example of the Clausius-Clapeyron equation to a water phase diagram, wherein we have seen that the phase boundary between the solid to liquid transition is moves towards left. And why does it do so? Because the molar volume of ice is higher than that of liquids. So upon increase of pressure, we see that the phase which has lower volume will be more stable, right? So yeah, so I think that covers all the topics that we had from this week. Since this week was mostly theoretical, so I decided to cover the fundamentals first, and coming on we'll be describing more and more practical based questions. So what we'll be having is the phase diagram equations, the phase rule, the lever rule, and all such equations, and we will be having numericals related to those. And hopefully we'll be covering those in the upcoming TA session. So this TA session will happen every Friday at 6 to 8 p.m. until the end of the course, and then towards the end of it we'll have another class for examinations as well. So this recording of this video will be available for reference for students studying after the completion of the course, and they can if they have any doubts related to this course or related to anything that has been described in this TA lecture, they can always put it up in the forum available on NPTEL, and me as well as the NPTEL team will be available for reviewing those questions and getting back to you your queries. So thank you so much.